So today I'm going to talk about in-context learning. This is actually the third or fourth talk on this topic in this seminar series, but the last one was more than a year ago. Hard to believe. So since we're about to start working on this in earnest, it seemed a good time to return to it. I'll make some more references to the literature because there's been quite a lot happening over the last year and a half or so in connection with in-context learning. I won't go through the entire history because we went through that pretty carefully in some of the previous seminars, the videos for which you can find on the webpage. So just to briefly recap, so in-context learning or few-shot learning, those are similar but maybe not exactly the same thing. Emerged as an important theme in some sense prior to GPT-3, but really became a big deal because this was something that GPT-3 just did out of the box, which wasn't anticipated. So I'll just refer you back to SLT 20, the note, and some seminars which were on the 26th. Oh, that was this year. Okay, for some reason I thought I was speaking about this January last year, but it's a year in AI time. But it was in fact in January this year. All right, so here's the outline. Okay, so there have been many papers on this topic since then. I'm going to say a bit about transformers, mostly just to set up the ability to say what I want to say about what I'm going to call pointed transformers. And then I'll go through some quotes about various points of view on in-context learning. And what I want to get to is just have the context to say some very simple things about what we might call the inner posterior. I actually expect this to be fairly short. We'll see. But really what I have to say is not very complicated, but I think it's an important set of ideas to have when you're looking at this topic. All right, so I'm going to ignore positional encoding and layer normalization and essentially just treat decoder-only transformers like the GPT series. As usual, my favorite reference for this is Fong and Hutter's paper, the first on the list of references there. So just quickly, so here's setup. Given a set of tokens, I'm going to write that sigma for alphabet. An embedding linear transformation from tokens to some vector space. An unembedding transformation from that vector space to a free vector space on the set of tokens. Those are going to be logits. And for each layer, layers just being the indices for the following data. There's some algebra you can do on vectors associated to entities. Using a transformation which extracts for each layer and each head from a vector in V, a triple QKV, where H is an inner product space and V is a vector space. Okay, and so just to recap the computational steps involved in actually computing the output from the input for a transformer. The input is a sequence of tokens. So to that we apply this embedding. That gives us the initial state of the entities. So the one superscript corresponds basically to the layer, and the subscript is the index for entities which are being processed step by step throughout the layers of the transformer. Then there's a sequence of steps here which are multi-head attention and multi-layer perceptron. The equation I'll give in a second. That's some intermediate state of these vectors. They're all in V. And then finally, we apply the unembedding to the vector for each entity at the final layer. That gives us something that is a real number per token. Okay, and then the prediction of the transformer is a sample for the next token. So the next token would go here. It's a sample from softmax of this guy. Now, there's many important details here in terms of the nature of the true distribution, the fact that it's a sequence, any prefix of which is also a valid set of samples to process, is important, quite crucially, I would say, in terms of the ability of in-context learning to be something that would emerge from a system like this. But this will do for now. Okay, so I'm going to say what this update step is. All right. So by E here, I mean ELH. And by EI here, I mean ELI. So I'm in some layer. I've processed the entities to layer little l. I apply this transformation E to the current state of that entity, and I get a Q, K, and V. These also depend on the layer and on the head. The update here is to add something to the current state of the entity. What we add is some learned function of the following expression. With some normalizing factor. Okay, so as I take j over all indices less than or equal to I, these numbers here don't add up to 1, but if I normalize them, that's with the factor z. Then those coefficients of the vectors v, so those are query key and value vectors. If I normalize them to 1, that's the factor z. Now, this is a bit of a lie because here I'm just sort of treating one head. So really, what you have to do is you have to take the direct sum over all h's. Okay, I don't want to confuse the notation with too many letters, but let me say this again so hopefully it's clear. So if I fix L, for each layer, there's many heads, capital H of them. For each head, I have an independent ELH with L fixed. So for each entity, I'm going to generate a bunch of query keys and values. Those will generate these terms with the sum, 1 per head. Then I'm going to concatenate those vectors, or take the direct sum, as we would say. And then I'm going to apply an MLP to that concatenated vector. And that's the update. So it's incorporating information in a fixed layer for every entity from all the heads. Okay. And then I do this multiple times. So that gives me, in other words, this here is EL plus 1 I. And I'm going to do that again. So as I said, I'm leaving off layer normalization here. I'm ignoring positional encoding. If you've got a keen memory, you may recall that in previous presentations of this relation, I've mostly just said the sum over J, which is also valid. That just corresponds to all entities attending to all other entities, but it's often used that you would have an attention mask. That's the name for this restriction here, which means that when you're processing entity I, you only incorporate information from entities at or before I in the sequence of entities. And this is what, along with the positional encoding, gives a meaning to the order on entities. Any questions?
You're also not using output attention output weights. I'm guessing.
Attention output weights. I don't know what you mean.
WO. So if you have multi-head attention, then you have a it's Q, WQ, WK, WV, and WO, where WO combines all the heads.
Oh, you could incorporate that into the MLP. Yeah.
But yeah, I don't think it's that important.
Yeah, I believe if I'm understanding what you're saying, but yeah. Yeah, so to be clear here, I'm saying direct sum over all the heads. It's not just a sum over all the heads. So the MLP, if you wanted to put a linear layer in front of that, that would, I think, function as what you're calling a WO. But I'm not sure. Okay, so to repeat what I said on the previous...
So.
Sorry.
Oh, I was just confirming what you said.
Yep. Okay. So to rewrite what I said on the previous board, so the probability of a token T given the input T1 through Tn and W here would be all the weights. So that's the embedding, the unembedding, all these E's, and some other things. That's the distribution. So this is what the transformer computes, a probability distribution over tokens, given these weights and these inputs. Okay. So I want to set up the sort of language with which to talk about in-context learning, following sort of my previous talks and also some of this literature which I cited on the first board. And I think it's useful to think about extending the definition of a transformer with a sort of set of things that you incorporate into the attention of processing every entity. And basically this is just adding the encoder back in. So in an encoder-decoder setup, you first process some tokens, and then you finish processing them, and then you incorporate the finished state of those processed tokens via attention into the processing of other tokens that are sort of live, whereas the previous ones are then, like, some set of tokens are sort of frozen for processing, and then you're processing other ones. And that's more or less what I'm going to say. This language of pointed is just from pointed space is a space with a chosen base point. It's kind of a way of thinking about this. So we mean a transformer augmented with some fixed base entities. Fixed in the sense they're not going to vary over training. Now, entities only enter into the update via their query key and value vectors, so if the entity isn't changing, I might as well just remember those. Okay, so with those given, the modified update is everything else is the same, except I'm going to change this to add a new term. Which is the second term I'm writing now. Okay, so think of the entity I. In every step, it's going to receive updates from all the normal entities, but then there's also these kind of special entities over here from which it's going to incorporate information. So if you're not used to this kind of diagram, you think of the message from entity J being the value vector Vj propagated with some weighting, which is given by these exponential factors. Okay, so I can identify a normal transformer as I described it, or a decoder-only transformer as I described it on the previous board. Yeah, it's not quite an encoder-decoder transformer, right? Because I'm saying the set B is just fixed, independent of any input, but sort of morally it's similar. So a normal transformer is a pointed transformer with B empty, more or less. So given a sequence of tokens T underline, and transformer I'm going to denote with curly T. A pointed transformer with base entities B I'm going to denote it by putting the B's behind a semicolon. So if it's just a normal transformer on input T, I'll write it like this. The weights are going to be left implicit. Notice on my other computer there's a bit of a lag between... okay, not only is there lag, but my iPad is disconnected. All right. Just a moment. While I wait for my iPad to return. Is that clear? So the pointed transformer just has some fixed auxiliary entities which are incorporated in every step into processing every entity. So clearly then the B's are basically part of, like, they're sort of like weights, right? Or rather, sorry, they're more like part of the architecture itself. Right? They're not varying. Okay, why is this like currying? Well, as you might know in functional programming or lambda calculus, currying means taking a function with n inputs and producing a new function with n minus 1 inputs by fixing one of the inputs to a particular value. Right? So this is kind of, if you think of the tokens as inputs, I mean, of course, a transformer basically has infinitely many inputs in the sense that it can process an arbitrary number of tokens, in theory. So if you fix some number of that infinitely many inputs, you're not quite fixing input tokens, you're kind of fixing the results of processing input tokens, these entities. Fixing some number of them produces a new function or a new transformer. And the class of transformers is not closed under currying, right? But pointed transformers are in some sense closed under currying. Because if you curry a pointed transformer in that sense, you're just adding more base entities into its set. That's another thing of the same kind. So this class of pointed transformers is kind of closed in a way that normal transformers aren't. Okay, anyway, that's just basically just terminology. Okay, so to get back to in-context learning, here's the idea. We suppose that the input T1 to Tn. So suppose we have a transformer, a particular configuration of the weights, such that on some inputs the following description is valid. That the input can be divided into parts, the first part of which I'll call the prefix, the second part the body, prefix, or you could call it the prompt. I don't want to call it the input because it's all input, right? So I'll call it the prefix and the body. And maybe I'll draw the diagram first and then write some text. So here's what it looks like for the transformer to process this sequence of tokens, just in general, right? I've listed k twice, k plus 1. So we're going to apply our embedding, then we're going to start processing these entities through multi-head attention, etc. And then we'll end up with some primed versions, i.e. this would be e to the L sub 1 through k for some layer L. I'll just write primes. So these are the states of these entities at some later layer. Let me suppose that in between here, there's only weak interactions. Or really, I mean, no interactions at all, right? So that usually this entity, when it's being processed, would receive in each step inputs from all the previous entities. But I'm going to suppose that those dot products are just very small, so that mostly there is no influence directly until some stage. And let me also suppose that these entities don't really change up until that stage, right? So this is some layer L. In case you think this is a bit fanciful, so I won't get time to describe the actual algorithms, but people have both hand-cooked up specific configurations of transformers that do things like what I'm about to describe, and also found that naturally these configurations are learned in order to process certain kinds of data, for example, a variety of linear regression kind of examples where these tokens encode x's and y's, some vectors, and the task is to predict some linear function of the input x. That's the y. So there's a paper on transformers learning gradient descent in context, which I've previously, I think, in this seminar described as not worth paying attention to, and I need to eat crow on that because I read that paper again, and in fact, I think it's a very good paper. I just misunderstood it, or maybe found it a bit fanciful. But then there was a later paper, which I guess we'll talk about at some point, which theoretically proves that under some conditions, this exact configuration in that paper on transformers learning in context gradient descent, the exact configuration of heads that they described there, not only, I mean, it clearly works to do gradient descent, but I found it hard to believe that this actually really was something that was, it seemed a bit artificial. But not only is it found in practice when you train transformers, but actually it is the global optimum, as some other paper proves. So I was very much wrong on that. Anyway, so this setup I'm describing here is not fake. This actually happens. I mean, it's a bit idealized still, but okay. So let me suppose that I'm processing some sequence of tokens like this. The early tokens, there's some division such that the early tokens get processed, the other ones are left alone in such a way that let me call this B. This, or some function of this, is then all that really is needed to process the remaining tokens. Okay, so let me say this in words. In such a way that the prefix affects processing of the body, meaning the actual function computed by the transformer as described. And I'm also going to just suppose that this remains fixed from here on in. So what does this look like? It looks like first you pay attention to the prefix, you do some computation on that, you compute some function of the prefix, which you might call the latent concept. I'll explain what I mean by that. Then you use that latent concept to do some computation on these entities. So these are then processed as usual, and you get down to this processed value, and you make your prediction. Okay, so let me put it in a box here. So the statement is that when you process the transformer on this sequence of tokens, it approximately looks like first producing a curried or pointed transformer, and then computing with that. Okay, because what does it look like to compute some sequence B of entities, which then remain fixed, so you're not updating them, they're just frozen, and then you just attend to them in order to update the remaining tokens? Well, the processing you're doing from layer L downwards is exactly the processing that's on the left-hand board. Right? So the pointed transformer is then computing the answer to what to do when you see this sequence of tokens, what the next token is. So that's here. Okay, so you can divide processing the entire set of tokens, the prefix and the body, into 2 steps. The first step is computing B, and the second step is using B to compute the prediction. Any questions? I'll give a kind of trivial example. But this indeed is the example that has been shown in many papers to work. Suppose the prefix encodes pairs. 1, 2, 3, 6, 12, 24. All right, so maybe those are like sequences of tokens, right? Bracket tokens, number tokens, etc., etc. And suppose you look at that, so that's T1 through TK, and the summary of that is the latent concept doubling. Okay, so the transformer which has that doubling as its latent entities just computes x maps to 2x. Right? If you feed in a body, which is just some sequence of tokens representing a new number, right? So that goes at the end here, and maybe it's 13. So that's tk plus 1 through tn. Then it will actually output 26. And then you get the idea. So the idea, I mean, well, the real point, though, is that you can have the same transformer, not some differently trained thing, but which, when provided with a different prefix, say 1, 3, 3, 9, 11, 33, could process that to compute a different latent concept of tripling. So that this curried version actually computes this. All right, this is what in-context learning is. It's the ability to do this. This is one formulation of what it is. It's not the only thing people mean when they talk about in-context learning. Okay, so I'll come back to that remark, but I want to point out what the parameter space is for pointed transformers. So unpointed transformers, normal transformers, they're parameterized by weights. Weights are points in the space of weights. Those are embedding, unembedding, those E linear transformations, etc. Okay, but this B, I mean, I've written it either as a sequence of entities or just as the function of those entities that actually matters, which is the query, key, and value vectors. But I have something in mind that's even a little woollier than that, right? Like perhaps some function of that, which is like the effective contribution in that sum on the previous board, right? Like somehow if you took that second summand inside those brackets and you had some effective version of that that didn't quite depend on all the KBs, and I actually don't need the Qs at all, do I? I don't need QBs because they're not receiving anything. So that's just some stupidity in my presentation. So you get, it's just the Ks and the Vs. But you could also have some effective version of that, which has got less information even. but that's the information that actually matters. Well, let me. At the risk of introducing an inconsistency with the previous slides, it's better to be inconsistent than dumb. So let's get rid of the Qs. Okay, so the B's are the keys and the value vectors for each of these base entities, and those live in direct sums of copies of H and V. And those are really now kind of like parameter space, right? So let's just refer to this as somewhat ambitiously concept space. Right, so that's where these sets of base entities live. I mean, that's some finite dimensional space if you've got some finite number of base entities. So pointed transformers. Are parameterized by W cross B, curly B. And that's a little bit sloppy because obviously I need to specify exactly how many base entities I'm using in order for that to be true, but I kind of want you to imagine this number being infinite in some suitable sense, and so that currying takes me from a point in this space. Yeah, is that clear? So pointed transformers are parameterized by this space. Can a prompt actually be arbitrarily long? Sure, why not? It's just a sum over entities.
That's in response to a question from Rowan, who asked in the chat, does anyone see why B should be finite dimensional if the prompt can be arbitrarily long?
Oh, it's not. But I'm saying it's fine. I mean, if you just have to put some kind of you have to make some sort of sums convergent, right? So you could take it if you wanted infinitely long contexts, you would just have to decay the influence of further away tokens in some way such that the relevant sums converge. So technically, there's no obstacle to making sense of that. So I just want you to accept infinitely many things. The reason to do it infinitely many is then that currying takes you from one space to itself, right? So this operation leaves you within the same class of models, which is pointed transformers with potentially infinitely many base entities.
Am I correct that you also need n squared compute where n is infinite?
Yeah, that's right.
And also, as a more practical concern, you need some positional encoding scheme that can go to infinity.
Yeah, I think that's not such a big deal. We just index from the last token. I mean, it's infinite in one direction, which is into the past. And if you use the positional encoding, which was indexed from there, I mean, of course, effectively, you can't have an infinite context unless you. I mean, you could just. I mean, there are many of the efficient attention schemes kind of try to do some kind of rank reduction in order to throw away things with sufficiently little influence. So if you just truncate that infinite sum past some level of magnitude, then I guess that would be a reasonable approximation to infinite length. Yeah. I'm not proposing how to build a transformer with infinite context length in practice. I'm just describing a theoretical construct.
Clear.
Okay. I've run out of boards. So next stop. Okay, so here's part one of the punchline. So what do we mean by learning in statistical learning theory? I mean, I want you to reflect on how profound it is that this is a kind of phenomenon that actually is happening. Because, well, this is what we usually call statistics. So in statistical learning, we usually think of learning in the following precise sense. Learning from data, given a model. As a map from samples to some distribution. So I'll take the situation we are modeling an input x and an output y. And I'm going to map from data to trained probability density P star, which is supposed to approximate the true density. So of course there's a variety of ways of producing those P stars. That might be just by figuring out some particular parameter and taking the predictions according to that parameter. But if you're a Bayesian, you'll want to take predictions according to something that appropriately weights all possible parameters, which in the case of, say, singular learning theory will be essentially quite different from using the map. Okay, now cast your mind back to the situation we were just describing, and I said there was something very special about the input distribution, which is that the sequences of inputs you're taking to a transformer, they're tokens. Every prefix of that sequence is also a sequence of tokens, and that's kind of a trite observation, but it's really not a normal kind of distribution to be considering, one with that structure. So the fact that prefixes of samples are themselves samples means that there's no strong distinction between dn and x. Because it means that if x...
Sorry, I just didn't understand what you meant by that, but I think I understand it as something like you could consider all of the data that you've learned from before you started this inference run. You could consider that to be an earlier part of the prompt. Is that right?
That's right. Or to turn that around, usually we think of dn and x as rather different because, dn doesn't have any, x is just a single thing, right? But in the case where x is a sequence of tokens, maybe it can be thought of as itself containing many examples. Right, because in particular it contains all the prefixes of itself, and if the transformer is processing that in a way that is somewhat, maybe it's better for me to explain when I've drawn the following diagram, then I can say what I mean. Okay, so here's the usual process, right? So we would think of ourselves as taking a set of samples, dn, and a new input. We would learn from that data to produce, let me just take the situation where we're just looking at a map parameter rather than the predictive distribution for the moment. We would learn from that some parameter, and then we would make our prediction, right, by doing something like this. Okay, but if x itself contains many examples, or can be thought of as being divisible into some part like what we were describing. And if I'm processing that x in the way that I was describing on the previous board, so that essentially the first k tokens, which I'm thinking of as somehow special perhaps, but I mean, in the case where I'm doing linear regression, for example, there's just one, the prefix is everything but the last. It was as I described it earlier. I'm about to say it in a less precise way, and maybe I'll retract that. So if I'm processing that sequence of tokens as I described earlier, so that the first k basically influenced the result only through this b, and then I'm computing something as a function of the final tokens, then I've got a factorization that looks something like this. iPad's disconnected again. Yeah, the rest of that line is coming. Okay, so what I mean by x and dn not being too different is that what do I do with dn? Well, I summarize it into a parameter that I then use for prediction, so that dn enters into the prediction only through wmap. Now, what I'm saying here is that x enters into the prediction only through the final part, tk plus 1 to tn, and not through t1 to tk. t1 to tk only enter insofar as they influence the latent concept b. Right? So in that sense, an x, or rather part of x, behaves more or less like more data, because data affects predictions only through learning, whereas the input is sort of treated differently. Right? So because of the nature of the assumption about the input distribution and a hypothesis about how the transformer is processing that information, there's something quite special about the nature of statistical inference for this system. Is that a bit more clear? Matt?
Yeah, that's clear.
Okay, so I want to say this behaves like WMAP in some sense, in the precise sense I just said. Okay. So let's think more about that. So the target of statistical inference, the thing that we're trying to extract from the process, is not in this case just W. That would be what pre-training is producing, right? It's producing some parameter. But actually, what we're targeting is W prime, which is this parameter space for, as I call it, pointed transforms. Okay, so if all that hangs together and is true for your particular true distribution and the transformer that you're running on it, then in this sense, the machine is doing statistics. In context, right? You feed in X, it's doing exactly the same thing you were doing on the outside to produce WMAP from DN, but it's doing it for the examples that are provided here. So which I'm going to refer to in the next part of the discussion as D hat K. I think there was maybe some questions in the chat that I missed. No, not a question. An awesome reference. Okay, so now I want to just briefly go through some quotes, which from some of the papers that I referenced earlier. Whoops. So if you'll follow me. All right, so This is on the topic of what is in-context learning. Section 3. Which I haven't defined. I don't think I want to define it yet, because it's kind of implicit what I mean. It's something like this ability to do statistics in context, but I want to leave giving a precise definition for some other time. But I'll go through some of the way people talk about it, because it's sort of useful. So this first reference is from the Transformers Learn to Do Gradient Descent in Context paper. It says an ability to flexibly in context learning, ICL, is an ability to flexibly adjust their prediction based on additional data given in context. Optimizing transformer weights can be regarded as learning on 2 time scales. Solely through the pressure to predict correctly, transformers discover learning algorithms inside their forward computations. Yeah, so that's the particular one is gradient descent. That's a way of inferring the B, right? So learning the map parameter, one way of operationalizing that form of Bayesian inference is to do gradient descent. So I'm not saying exactly how the transformer is processing the prefix to produce the B, but in particular examples, you can see that transformers actually do implement in context forms of optimization algorithms that we also have learned to do when we're doing statistics. The second set of quotes is from, let me check. Xie et al. An explanation of in-context learning is implicit Bayesian inference, which is very much along the lines of what I'm saying. I think you should view these statements as speculative in many cases, but there are particular, very precise examples where this is known to check out. So it's still very early. The story is very early in terms of whether the broad assertion that in context statistics is taking place, the jury is still out on that statement in broad generality. But in, for example, linear regression, this is very well established that transformers can not only theoretically do this in the sense you can author weights by hand that make this work. That's not that impressive. Function approximation, blah, blah, blah. But the fact that actually, the training processes we usually use to train transformers do easily find algorithms that look very much like the ones we would hand design if we took our knowledge as human statisticians and baked into the transformer that process. That has been verified in a small but kind of compelling list of simple examples. Just to refer to the difference between various things that people mean by in-context learning. So in the GPT-3 paper, they don't refer to in-context learning, if I remember correctly, but few-shot learning. That was the term that most people used. That's where you take this input-output perspective. That was the perspective of my example, right, with the 1 in and 2 out. So the XY pairs, that was the data set. The perspective where you supply a bunch of examples of the task you want to perform, and then you infer a latent task or latent concept, and then you're given another input and you have to produce the output. That's the paradigm in which a number of these papers are written. An exception is Olson et al., the induction heads and in-context learning paper, which is one of the most important empirical works in this field. They think of in-context learning differently, and sort of more, you could say more generally, as being a difference. Well, so obviously the point of having a long context window is that you have more context, you can do better prediction. So it's not a surprise that if you go further along in the context, you'll do better in the sense that, or rather further back in the context. So if you're trying to predict the next token given 3 words of English, it will help to see the previous 10 words, right? So the difference of token losses at different points in the context should decrease as you go further along in the context, or better off to think of it as adding more context to the beginning. Okay, that's not a surprise, but the fact that that difference in quantity might become a difference of kind as you train the transformer is one way of thinking about what in-context learning is. That's consistent with the description earlier, but in principle seems a little bit different. Go ahead.
No, just nodding along. Yeah, I think that's an important distinction that tracks like some of the ways I see different people talk about in-context learning differently. What could you maybe comment on the difference in kind? Like, is there a situation where you can actually view the helping to predict the next token in what doesn't really outwardly appear like a learning problem, like it's not a sequence of examples. So having 10 tokens beforehand is more helpful than having 2 tokens. Could you also just view that as like passing along some like a currying thing, or like passing along some concept parameter?
Yeah, I think the precise connection, it's sort of implicit, but I'm sure many people understand what I'm about to say. So in the in-context learning and induction heads paper, they talk about, well, induction heads, right? And they distinguish between like a very precise kind of induction head that sees A, B previously and then sees another A and predicts B, from something that's like a fuzzy induction head, right? And they write something like this. So a fuzzy induction head is supposed to, you're looking at A, previously you've seen something like A for some definition of like, and so you're going to predict B where B looks like the thing that was coming after the thing that was like A. Now, so the bridge between the difference in quantity becoming a difference in kind, and the per token losses at different points in the context, and the sort of few-shot learning story, as far as I can tell, is that the few-shot learning story is very similar to this fuzzy pattern matching. So it's more like the mechanism by which they see the difference of kind arising, namely induction heads, can be pretty clearly thought of as related to the story I was just telling, right? Because if I were to give you a bunch of examples of inputs and outputs, and then I give you a new input, well, let me take all of this and think of this as my kind of A star, and take all of this and think about it as my B star, and this is my A. Right. So A is similar to A star because it's sort of, I mean, I obviously have to recognize what an input is. And then the B stars, I mean, you see what I'm getting at, right? So I think this fuzzy pattern matching idea sort of incorporates the idea of few-shot learning. And it's this relation between the notion of similarity between B and B star and A star and so on is sort of, it's kind of incorporates this idea.
I guess my question is like, is it maybe like trivially true that you could always view what a transformer is doing in this way if you like have a convoluted enough concept of concepts and your B parameter? And so what we're looking for is something more like cases where this actually turns out to be IID, like working under some kind of IID assumption or doing statistics in a way that we would recognize as statistics, or using certain algorithms for doing the predictions in context. Is that the idea?
Yeah, I think that's right. That like if you took that period where there was no influence from the sort of prefix to be 1 or empty, then basically just whatever happens to the first K tokens could be thought of as the latent concept. So there's some limit where it becomes tautological. But that has to be the case in some sense if it's discovered by gradient descent, right? So that's not a surprise. So how do you recognize when it's actually happening? Well, I think that's a difficult question in general. I mean, obviously the appearance of induction heads in a phase transition and the relation of that to this idea is, maybe it's just all induction heads, right? Maybe that's the answer. I would say it's better to focus on the emergence of recognition of particular tasks. So, like the early stages of the appearance of this might be harder to understand than if you like the acquisition of new latent concepts is probably the easiest place to look for in terms of actually understanding and being able to argue that something like this is happening. So maybe also ultimately it's a statement about factorisation, which is what I'll get to. So maybe that's the place to make the reply to this. I want to wrap up in the next 5 minutes. Let me see what this quote is. During pre-training, transformers learn a prior over latent tasks represented in the pre-training data. When prompted with examples at inference time, they retrieve relevant pre-training tasks and generate subsequent tokens from the posterior distribution. Yeah, this seems like a very strong statement. I don't like retrieving relevant pre-training tasks. This is a natural way of thinking about it, perhaps. I'm not sure I really want to sign on to such a strong statement. Yeah. So these are like, well, as you know from the deep learning, machine learning literature, you in math, you never write the folklore. The folklore is completely unwritten, and it's only in the verbal form of the subject. In ML, it's the other way around. The folklore is the only thing you write down. Well, not quite. But, you know what I mean. Okay, so I want to move on from... I like this paper. That's not a criticism of this paper. And, so here's... do I need 2 boards? No, I think 1 is fine. Okay, so here's what I want to end on, which is a kind of refinement and summary of this story. So in an idealized form. It's a bit similar to what's in the paper X. So the picture is of W. We think of W in normal statistics as parameterizing models, and models just as being things that make predictions. No more, right? That was true before 2020. We're not in that world anymore, at least not with transformers. You should think of W not as a space of probability distributions, but as a space of statisticians, right? Of maps from data to probability distributions. At least if you buy the story so far. So I don't know what to call such things, but let's call them meta-parameters. Just hyperparameters, I guess. That is, we're thinking of them as methods of mapping in context samples to predictive distributions. And it's really this factorization into hierarchies that is the interesting thing mathematically here. I really do think this is quite a profound. The fact that this happens naturally is really quite profound. So here's the input I want you to think about. So we've got a pre-training data set. So this is just, the pre-training distribution, the true distribution for training our large language model, say. I want you to think about d hat as being some prefix and x as the input. Okay, but this is my T1 through Tn, right? So this is the thing that's going to go into the transformer, say. And I'm putting the hat there to subtly remind you that the distributions may be different, right? It's not like when you're training on internet text, you see a lot of input-output pairs for English to French translation, right? You see English language and you see French language, but you don't see a lot of examples of input-output pairs and then people putting an English word, right? That isn't the normal, that's not part of the true distribution of internet text. Okay, so what do we do if we were to think about Bayesian statistics of a large language model? We talk about the posterior, which is determined by that pre-training distribution. That's a distribution over parameters, but I want you to think about it in the sense I've just explained as parameterizing ways of mapping these in-context data sets to inner posteriors. Now, it's not really clear why I'm putting a probability distribution over these latent concepts here, right? Because given the sequence of tokens T1 through Tk, we just got a B, right? The way I wrote it, B was just these entities processed up to some stage. But if you look at the actual algorithms that people have implemented to show that transformers can do something like predictive distributions over models internally in context, or if you just think about it a bit, you can see that it's not difficult for this B, this curried thing, the thing that makes the pointed transformer, it's not too difficult to arrange for that. I mean, it's ending up as it's determining a probability distribution itself, right? This attention distribution. So if I shift my way of thinking a bit, it's reasonable to think about this as being a distribution over B's. And I can clarify that a bit later if I think it's a bit terse. Okay, so this part is normal learning, right? Statistical learning. We're going from the data set D infinity to the posterior or the predictive distribution. I haven't done anything to this stuff yet. Okay, I'm just thinking about it a little bit differently because of this inner posterior business. To actually make my prediction, I'll just skip a step that's in the notes. So to predict, I can think about as factorizing in the following way. Predicting the output given the latent concept and the input. Predicting the latent concept from the current, or from the weight that determines the transformer. And I need to know what the probability of that weight is given the pre-training data set. Okay, so this is like the inner predictive distribution, right? If you think about B as being a bit analogous to W. And this is the abstraction step that is telling you how probable a latent concept is given the in-context data set. And this is the sort of outer posterior. Right, so that we factorize the integral as a push forward involving concept space. And it's this factorization of the integral into, rather than two parts, into three, introduces this higher order space, and it has a corresponding hyper Fisher information metric. And yeah, there's sort of a lot more one can say in that direction. If you look at DLT3, there's some comments about hyperfisher and conformal transformations and stuff. So, and there's an accumulating experimental and theoretical picture behind the validity of this kind of factorization as being somehow a good way to think about in-context learning. So if I say inner posterior, of course, that's partly motivated by posing the following question, which is, what is inner SLT? Yeah. If we're computing inner posteriors from in-context data sets, what about inner phase transitions? What about inner phases? What about inner free energy? Are transformers doing in-context model selection according to some kind of free energy formula? I don't think these are crazy questions. And I'll stop there. Thanks. Questions?
Thanks, Dan. Does it depend on like the task that we're getting them to do? Like in these toy tasks, for example, if you try and get a transformer to do just linear regression, is that gonna actually encourage the transformer to learn during pre-training to do SLT?
Yeah, good question.
Or where yeah, that's my question.
Yeah, I have no idea. I mean, as you know from looking at this literature, I'm guessing you won't see this in context learning at all if there's not more. I mean, if the task distribution, if there isn't more than one task, and if the task distribution isn't sufficiently diverse, you won't see this behavior emerge at all. So there's sort of a little bit of literature on what it takes to induce in context learning, and you certainly need. I mean, the outer model selection, Occam's razor, would say that you shouldn't do some crazy thing like in context learning if there's a simpler solution, like just learn the mapping. Yeah. But if that's somehow
exactly,
yeah, but there's so I don't know theoretically either how to characterize like what what we're seeing here is something like, there's a phase transition, presumably, when the in-context learning begins, and conjecturally, the induction heads story would say that that is what they found, where the induction heads appear. And I find that actually pretty convincing. There's a lot of evidence in that paper, so I'm inclined to believe that induction heads are critically involved. So actually, one of the main it seems like obvious things to do is to look at some of this literature on linear regression and in context learning and find induction heads. And either you fail to find them, in which case that pretty much argues against the case of universality of induction heads as being an explanation of in context learning, I would say. Or you do find them, and that's strong evidence for that assertion in a sort of synthetic setting, apart from the synthetic one that they study there. But if you don't have... okay, so what was I saying? So you would expect that there's a phase transition in which this in-context learning ability appears, and in fact the task diversity paper that we've been talking about briefly sort of goes in that direction. It seems to argue that, in fact, there's a critical threshold of number of tasks past which this will happen.
I don't want to take up the rest of the time talking about it, but it seems to me in the task diversity paper, at the low task diversity, the model is already doing a kind of in-context learning when it has to figure out which of the training tasks it's being faced with at testing.
Yeah, I would agree. Other questions?
Thanks heaps, Dan. It was a very interesting talk.
Yeah, thanks.
Quick one, Dan. This could be a very simple, and it will be a very simple question, but in all the papers when they say like doing Bayesian inference, can you clarify what that actually means.
When they say the model is doing Bayesian inference.
Yeah.
Yeah, to be honest, I don't think they know. I think it's not clear there's a mechanism. I mean, it's not clear they really want to say that in some very strong form. I mean, like the quote I was just referring to earlier, right? Like, I think what they mean in some circumstances is, oh, you're talking about the task diversity one? Is that what you mean?
Yep, that's one example. I just say get bandied around a lot.
There's a precise meaning to what they're saying, which is that they are asserting that, at least in terms of its behavior, the transformer is matching the Bayes optimal algorithm or function for prediction, and in that sense is being Bayesian. So it's like a behavioral thing. That in other papers in this literature, like the one I was citing from, is sort of in line with the assertion that algorithmically it's Bayesian, in the sense that a Bayesian would take the data set, compute a posterior distribution, use it to compute a predictive distribution, and then predict. So the paper X that I'm citing is asserting that, in fact, that is like algorithmically what is happening. And yeah, like there's some preliminary evidence for that. I wouldn't overstate it, but you know, like maybe that's sort of justified in some very limited examples. But that's obviously a much, much stronger statement to say it's being Bayesian in that kind of sense. Yeah.
Mm-hmm. And one other question, in terms of this idea that in context learning is the same thing as doing gradient descent, do you think or expect that studying phase transitions in context learning then gives you a prism through which to view phase transitions in gradient descent?
We'll restate the question, please.
If there's this correspondence between doing in context learning and doing gradient descent, which I'm still very much wrapping my head around, but since we're seeing these phase transitions in context learning, do you think that provides a window into studying phase transitions in gradient descent using that correspondence?
I think I have to say no, but I'll try and so the way in which gradient descent seems to happen in some cases in context is as a means of computing the B from the D hat K in my notation, right?
Mm-hmm.
So it's basically just like the way, I mean, suppose you come to machine learning as a Bayesian, you would say, well, really, I believe in this distribution, but to compute it in practice, I might do gradient descent, right? So that's the spirit in which you think of the model as maybe instantiating gradient descent as a particular learning algorithm with the aim of achieving this B or this inner posterior.
Mm-hmm.
I don't know that it says anything to me about gradient descent. Yeah, so I think I would just say no to your question, but maybe I misunderstood it.
Mm-hmm. No, sounds good. Thank you.
Further questions? If not, we'll move into going around the circle again. Speak now or hold your peace. Okay, then you are holding your peace. All right, thanks everybody. I think it was fun to stand in a circle, so let's see if we can manage that. You have 5 seconds or I kick you if you're not in the circle. My fingers are poised on the keyboard. /kick. Is that a circle? Liam, you're not in a circle. Yeah, okay, that's pretty good. Okay.